OK，好的，各位同学，那我们开始上课哈。For this week, we will use the online course for the detection and estimation. So let's begin here. So last time we talked about the likelihood function. So let's take a look at the screen and let's see how uh, the likelihood function is working. Okay, so let's take a look at this example. So we have a PDF dependence on the unknown parameter. However, the signal model looks like this. You have a data equal to A plus noise. And that noise is distributed by Gaussian. But let's take a look. If we write out the PDF that is P of X condition on A equal to this multiplied by exponential of this minus 1 over 2 sigma I squared. And how come we are having this I sigma I? Because we like to discuss the possibility of different values of sigma I. So in other words, if that sigma is different, then how would the PDF look like? That will be uh, the way we look at the problem. Okay, so uh, there is this unknown parameter A, and at observation, the value of sigma 0 is given. Okay, so let's see if we take a measurement that is x equal to 3, and then sigma equal to 1 over 3, and what's going to happen? Let's take a look at the figure. So the figure is over here. We have this PDF, and after observation, we have theta equal to 3, condition on A. As a result, you see we are plotting the PDF versus not the X, but the value of A. Because let's take one step back and see if for this equation you already have observation X, then what happens is the only unknown in the equation is A. As a result, we see this as a function of A. So we plot it versus A. And then the other case is sigma equal to 1, and you have a more wide spreading, the spreading out effect for this PDF. Again, we see it as a function of A. So as I mentioned, when we see it as a function of A, this is what? This is like a PDF, but it in fact is a function of A. As a result, we will like to call it the likelihood function of A instead of PDF. Let me emphasize again. For this kind of function, we like to call it likelihood function of A instead of PDF. This is very important concept to introduce the likelihood idea because there is a distinction between likelihood function and PDF. If you integrate that area, this whole area, it may not be 1. So it definitely will not be a PDF. A PDF, when you do the integration over its domain, it's got to be 1 because the probability is 1. But likelihood function it may not be 1. Okay, so that would be our idea of thinking about the so-called likelihood function. So let's, without the details, let's go to here. When the PDF is viewed as a function of the unknown parameter with x fixed, how come, as I mentioned, with observation x is already fixed, right? For example, you take a measurement, it's 3. But next time you take a measurement, it could be 4 or any number. But after observation, x is fixed. Then we call it likelihood function. Here, likelihood function. And 2 examples of likelihood function are shown in figure 3.1. Okay? So up to this point, we have introduced the likelihood function. And I guess you need to be familiar with the concept because you are going to use this a lot in terms of this class or in terms of your research. I think you are going to have a lot of you know you're going to have experience a lot in terms of the likelihood function. Okay, so let's take a look again how the likelihood function is looking. So if you have sigma 1 for this 1/3, right, sigma 2 equal to 1, you know the sharpness at the tip of the likelihood function, the tip at the top of the likelihood function. That's where you decide the value of A, right? For example, let me take a simple example. If I'm asking, looking at this likelihood function, what value of A will you take? Most likely, we are going to take the 3 because 3 corresponds to the highest point in the likelihood, right? It corresponds to the highest point. In other words, that's the maximum point in the likelihood. And it's the same here. But however, when you have disturbance, you kind of making small errors in around the mountain top. So the sharpness of the likelihood function, particularly at the top, implies the accuracy of your estimation. So let's take what textbook is saying. The sharpness of the likelihood function determines how accurately we can estimate the unknown parameter. So for example, this is sharper than this one. So if you are to make a mistake, you probably make a mistake around the area. But you can make a mistake for a larger area here. So the sharpness determines the accuracy of the estimation. Okay. So to quantify this, the sharpness is effectively measured by the negative of the second derivative. This is from calculus. 从微积分来的一个概念，就是 likelihood function 这里尖端的部分的尖端程度，就是二阶微分的负号取负号。Okay. So the logarithm of the likelihood function at its peak, this is the curvature, terminology of curvature of the likelihood function. So again, we follow that example and consider the natural log of the PDF. We take the PDF and take the natural log, it becomes something like this. Then take the first derivative. First derivative. So we will just use the basic calculus technique and then make the derivative. And then the second order derivative. In other words, you take the derivative with respect to this again one more time. You do it one more time and then take the negative. So you get something like this. So the curvature increases as sigma squared decreases. Since we already know that the estimator A is equal to x0 has variance sigma squared, then for this example, variance A estimator will be just the negative, right? It has variance sigma squared. So if you take this term and put it into the denominator, it will turn out to be sigma squared, which is equal to the already known sigma squared here. Okay, so the variance decreases as the curvature increases. Does that make sense to all of us? I think yes, right? Imagine, let's take a look at the sigma model. If you have a small small variance in in the noise, you're going to have more accuracy in estimation, right? So that is consistent with the idea that your estimator has sigma squared as a variance. In other words, if you have small variance in the noise, it's more accurate. And it's reflected in this equation. Okay. So although in this example, the second derivative does not depend on x0, in general it will. So a more appropriate measure of the curvature is you have this second order derivative and negative, then you take the expectation. So in other words, we are taking the average curvature, and that will generally be the lower bound of the estimator. The lower bound of the estimator. Okay, so here, uh, yeah, that measures the average curvature of the likelihood function. The expectation is taken with respect to this, resulting in a function of A. Okay, so the expectation acknowledges the fact that the likelihood function, which depends on x0, is itself a random variable. The larger the quantity, the smaller the variance. Okay, so now we will formally go to the focal point in this chapter, Cramer-Rao bound. So the description looks like this. It is assumed that the PDF satisfies some regularity condition, which is expect for the first order derivative equal to 0. That sustains generally, if without special cases, generally that regularity will sustain. So we are fine with that. Where the expectation is taken with respect to P, then the variance of any unbiased estimator must satisfy variance theta hat larger than 1 over expectation of second order derivative with negative sign. So this is the called the lower bound of the estimator. So let's take one step back. You see, we have variance equal to this, but generally it will be like this. So formally, CRLP is telling you that this will be true, where the derivative is evaluated at the true value of theta and the expectation is taken with respect to P. Furthermore, an unbiased estimator may be found that attains the bound for all theta if and only if first order derivative equal to I theta multiplied by g of x minus theta. Okay, so let me repeat one more time. Unbiased estimator will be found if you take the first order derivative and you can put that first order derivative into this kind of format, meaning you have a function of theta only and then g of theta only minus your theta. So for some functions g and I, the estimator will be the minimum variance unbiased estimator, which is good, right? We mentioned many times we like NVU. It's minimum variance and it's unbiased and it's all good, so we like it. So this is the way to find the NVU estimator. So if you can successfully find this equation, then theta hat will be g of x and the minimum variance will be 1 over I of theta. And the expectation is explicitly given by expect of this equal to this. This is just to write the expectation out. So formally, this will be CRLB. So let's take a break, and then in next session, we are going to take a look at an example.